So this is the solution for number 5. This solution is quite lengthy, so make sure you have a lot of room on your page. For a matter of time, I'm not going to work out every step of the calculations when we do cosine law, but I'm going to show you how to set this up and work through your solution. So the first thing I did was I drew the scenario using all of the vectors. So I want to know the distance from the parking lot to the rest cabin, given that this is how the ski group determine their trip. So I'm going to put a P here. This is the parking lot, and this is the rest cabin up here. I'll put a C up for cabin. I want to know the direct distance from P to C, given some direction. The problem is we have 4 different vectors that we need to add together. And how do we do that? Well, we're going to look at a combination of 2 vectors at a time. We can only add 2 vectors at a time, so this is why it's going to take a little while. Let's start with V1. Vector 1 was 3 kilometers west. So V1 is V1, 3 kilometers. I'm going to use absolute value signs here to denote that that's just a magnitude right now. Then they turn northwest. Now, when you're given the direction as northwest, you're going to assume that it's always 45 degrees from the vertical or the horizontal. That's how I got 45 degrees there. So V2, the magnitude of V2, which is this vector, is 2 kilometers. Then they turn east, which I'm going to call V3, and they travel for another 3 kilometers. And then they go due north for 4 kilometers. Now I'm going to call that V4 with a magnitude of 4 kilometers. So how do we solve the problem? Let's start by adding the first 2 vectors. You're going to find the resultant of V1 plus V2. Now I'm going to write your steps here. So step 1, you're going to take V1, you're going to add it to V2, and that's going to give you a resultant vector R. Let me add vector symbols here. Now, you're going to take the resultant from V1 and V2, and then you're going to add it to vector 3. So R1 plus V3. This is going to give us our second, we'll call that R2, our second resultant vector. And you can try to visualize how this is going to happen. Right? R1 will be the vector that extends from here up to there. Right? There's R1. You're going to take R1, add it to V3. Now think about what this resultant is going to look like. It's going to be over there. There's R2. And then finally, for step 3, you're going to take vector resultant 2, and you're going to add it to V4. And that's going to give us a third resultant vector, which I'll draw in red again, from P extending up to C. Okay. So there's R3. That's what I want. We're after resultant 3. So let's get started here. I'm going to go to a new slide, and I'm going to do step 1. So for number 1, we need to do V1 plus V2. Now again, you can sketch it again to get a better picture of what's going on. We have a vector going this way for 3, and then we have a vector going northwest. So think about what this angle must be, right? We can draw out a little compass here to help us, and I knew that that angle there was 45 degrees because it was heading northwest. So I know that this whole angle is going to be 90 plus 45, which is 135 degrees. Okay. So your resultant vector is from the tail all the way to the head. And again, these are just sketches. You can draw them a little bigger and more neatly on your page. R1, using cosine law, squared. We know these magnitudes given in the question, so 3 squared plus 2 squared minus 2 times 3 times 2 times the cos of 135, we end up with R1 being 4.64 kilometers. And again, eventually we're going to need some direction here. So again, let's label that theta. You're going to use sine law to solve for theta. And again, for a matter of time, I'm going to state the answer. Theta is 17.75 degrees. So now we have to take this resultant vector and we're going to add it to vector number 3. I'm going to go to a new slide and let's call this step 2. We take vector 1 and add it to vector 3. Now what does that look like? So R1, if we remember, has a magnitude of about 4.64 kilometers, and we knew that the direction was west 17.75 degrees north. So let's draw this vector. It's going to be roughly in this direction. We know that we draw a little compass. This is 17.75 degrees, and I can easily find that other vector there. And then we know that V3 was 3 kilometers headed in that direction there. So we want to find the resultant of those two. Now I drew that a little bit too long, so let me erase that a bit. There's that. So I want the resultant. I'll draw the R that you're going to solve for. It's going to be up here. We'll call that resultant 2. And again, you're going to have to look for a theta value for a direction, but we'll leave that to the last step. Using supplementary angles, you also know that this angle up here is 17.75. And that's going to allow us to solve using cosine law. So we know that the magnitude of R1 here is 4.64. We know that this is 3. So R2, magnitude, use cosine law, 3 squared plus 4.64 squared minus 2 times 3 times 4.64 times the cos of the angle between them, which is 17.75. Solve all of this, and R2 has a magnitude of about 2 kilometers. And again, we're going to need some direction. So if we're looking at this carefully, we're thinking, well, if we know this is 17.75, how can we solve for another unknown angle? We can very easily solve for theta. Theta sine theta over the opposite side, which is 3, equals, we can use the sine of 17.75 and divide that by the magnitude of 2. And solve that, and theta ends up being about a little more than 27 degrees. So that's where theta is. Now I'm going to highlight this angle because we're going to come back to it in the next slide here. We know the size of the angle I'm highlighting in green, and we'll see why that's important. So step number 3, we have to take R2 and we're going to add it to vector 4. So draw R2 again. Again, it only has a magnitude of 2. Draw it up like this. And then we need to draw a vector of 4 kilometers due north. So that's that there. And I want the resultant. This is our third and final resultant from the parking lot all the way to the rest station there. So there's R3. So here's where we're left with this dilemma that we don't have an angle to work with. Well, remember from the last slide I highlighted in green an important angle, and I'll show you why. I'm just going to draw a little compass here to help visualize this. I know that this is 90, and I also knew from the previous slide, and I'll show that in green, that this angle here to a horizontal was about 45 degrees once we add 27.2, and if we go back 17.75. This whole angle here in green is 45 degrees. So that means this is 45 degrees. Well, if that's 45 degrees, then I also know that this angle here is 45 degrees, which means I can take the angle that extends from V4 to V2 as being 90 plus 45. And that gives me 135 degrees. So now I can use cosine law and solve for R3. So the magnitude of R3 is going to be 4 squared plus 2 squared minus 2 times 4 times 2 times the cos of 135. And what we get for our final resultant is about 5.6 kilometers. Now what you need to do is give some sort of a direction. Now what I want to do, and I'll use yellow again, is to find this angle in here. I'm going to label that theta. We can easily do that again by sine law. So sine theta over 4 equals sine of 135 over 5.6. Theta ends up being 30 degrees. So now think about it. You know that the angle from the vertical is going to be 90 minus 30 minus 45. And that gives us 15 degrees. 15 degrees is going to be the angle between, I'm highlighting it here in yellow, our resultant R3 and the vertical, which is that green dotted line that would extend up. And that's important because it gives us the direction for our final vector. So to write your final answer, you want to say R3 is 5.6 kilometers north, 15 degrees west from the parking lot.